Assalamualaikum warahmatullahi wabarakatuh. Let me introduce myself. My name is Muhammad Surya Putra, and I'm here for the final exam of second computational physics. Before we dive deep down into my topic in here, I want to thank my lecturer first, my dearest Mr. Sugianto, for this half semester, and of course for if my friends, all of you guys here enjoy this video, and let's get into it. The first one is we gonna talk about the we're gonna talk about the equations of differential partial of the partial differential equations. So I want to show this. Okay. Okay, wait a second. I guess we have a slight problem here. So I'm gonna okay. We serve problem we already been served by a problem that we encounter. So the problem we encounter it's based on something like this actually. Like it's based on this problem. So because I am from class B1 and I have the student identification number is even, so I get this this plate, this metal plate of square, and then this is the problem. And get let's get this done. The problem. So the problem we encounter is the heat transfer. Heat transfer trans transfer or heat flow, I guess. Heat flow over the dimensional metal plate. So let's assume this is an iron, an iron plate, metal iron plate. So I think I'm gonna iron. So the iron itself has the conductivity thermal. So this is gonna use on that. So we have a square iron iron plate with with one side with one and side is uh has temperature of temperature temperature of 101 degree Celsius. And because we generate uh the random number is 17, so I'm gonna make it as a top side of the side of the plate. So 17. So and the top side has the temperature of 17 degrees. And the has plate side slang by 22, no, 20 centimeter, 20 centimeter. Now, suppose, no, 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 suppose. And then the assignment is analyze, no, analyze. I think this is not beginner. Analyze analyze the analytic, analytical problem, like a solve, method, method, and then analytical method, and also use the numerical method, numerical method to make a program on Octave to solve the distribution distribution of the heat over the plate. So the analytical one, let's get into the analytical one because this is really theoretical, analytically the analysis. So that we know that this heat transfer or heat flow is one of the diffusion functions of the diffusion equation. So diffusion equation of heat of heat is the functions of elliptic. Because what? So this is like two-dimensional. We have the differential of the function u by the positions of x and the element of y equals to 0. So this is two-dimensional heat flow a x is based on plus PE. So so we get we have the PE x as this is the second derivation, differential of the function u, the function u by the x. I'm gonna make it. This is really, we know this is the official, like the mainstream equations of Laplacian. Actually, in like two-dimensional heat flow, this is very mainstream. And then these both are the functions of u is differentiated by uh twice differentiated by the x and of course the element of y because this is two-dimensional is equal to 0. So why it is elliptic? Because okay, let me show you. And analytically, this equation would be uh, calculated by, also we're going to calculate or analyze these equations by variable separation method, by variable variation method. Method, and we get, let's, x and y is equals to the x is the functions of x and the y is the functions of y. This is the separation. So, in this heat flow scenario, dx, the u functions is become t functions because this is temperature distribution. So yeah, this is the temperature distribution or heat distribution on a plate in plate with the element of x and y. And we have, of course, we already have the boundary, and then with boundary, so if we have this boundary, and the boundary is, let's say, from the x is equal to 0, is x equals to 0, when the y is for 1 to n, let's say this. Yeah, I'm gonna say this. From 0 to n is equals to 0. Yeah, this is equal to 0. And of course, this boundary is not, uh, this boundary is not related. It's not like, not specifically uh in equations, but it's specifically on the case. So in this case, because my n is not 0, so I would say because my n is like 22, 22, and then I have the bias of 17, I have the PS of something on the support of 17, the subtract of 17. So yes, I'm gonna say 17 or 16 because the 17 one is still in the top. Then I have the x is zero, when not zero. The x is zero to the n. I was actually gonna say 60. Mm. Y equals to zero. And this is not zero. This is 17 degrees Celsius, as we know before. And we get the Tx. And the x of 17 is 101. Wait, am I wrong? Oh, no, 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 no. This is zero. Oh, no, this is not zero. Yeah, it is zero. It is zero. And then we have this, and this is the 17. And it's all of it became 17. This is the top one, the top side. So we have this temperature of 17, and the side is like here. This is a 17. They have different temperature of 17 degrees Celsius, and this is have the temperature of 101 degrees Celsius. And this one, and this end has the temperatures of zero. So this is the boundary. And because of that, we knew this is ST E. So we all know that this is the differential equations. This is differential equation. So we're gonna make it as a differential equation. So let's run to x1 is the y1 plus since the x1 equals to zero, of course, again. And then so in this case, the this side, this side, we're gonna subtract to this side, we're gonna move to this side. So we can get the equations of this. Yep. This is the x1 equals to the y1, differential, the second differential derivative of y divided by the functions of y is equals to what we call as the lambda. Let's see the lambda first. Do I have it? No, I don't have it. Okay, this is the lambda. So we get the expression in our this. This equals to 0. Then force the y side, the y element is equals to 0 also. Because the BDE is elliptical equation. And we knew that the lambda is more than 0, not lambda, the determinant. The determinant, okay, let's say the determinant is already 0, so we know this. Lambda is equals to this. This is an iteration one. It's more likely to become numerical because yeah, this is analytic is not like about it is not numeric or it is not numerical or this is just analytic. No, the analytical is how we uh view this as a phenomenon, and then we can calculate it. And the method of calculations can be numerical, computational, and the others that existed. So yeah, in the pi, where's my pi? The pi is 2 as well. It's also a 2 as well. And then we got the solution. Solution. This becomes so interesting, you guys. This is become Fourier transform. And it's a little bit, you know, we have the x first, the x element. Of course, it's the functions of x. It's equals to and this is the s. Okay, the s is actually the side, the length of the side. So yeah, this is the s, the length of the side. And then we have the overview. Is the example in here is actually not really representative because it's just I make it as broad as possible because yeah, because analytical sometimes is more difficult to understand than the numerical one. Numerical sometimes just yeah, this we get this from this and from that. Yeah. So this is a little bit difficult, but it's all right. And then because the yn is 0 in the 0 can be 0. This is sorry. The scenario is basic. We have this basic and universal scenario that the yn is 0, and then we choose the an is also 0, and then we calculate the bn. So this is, I'm gonna take it as 1, and then we have the an is, of course, the 1, because this is, we assume to for, we actually to choose the an or bn, but the cost, and the cost is 1, and because this cost h of np per y per s y, when the y is 0, the cost is not all, it's not, and it's not the, it's not 0, but it's 1. And then of course the sin, if the sin 0 is, the sin y is 0, so the bn is also 0. This is just common sense. So the n is also 0. And then we got the bn. The bn is equals to, okay, fine. This is more likely to be more difficult, more like complicated. Okay, the y is, okay, this is the bn, the value of the bn. And of course with this, if we have the dx, dx when the y is 0 is dx, yeah, I think I'm gonna, the y, of course, the variable y in the y of 0 is also included. So this is the one. So the, because the yn is 0, so just we just get the value of the xn. The xn is, okay, fine. Okay, this is 0. I get, you got it right. So we got the equations as this one. And then we get the fx. This is the f of the x is, the functions of numerical is n to infinity. And of course, this is a constanta, the bn, but not bn this. This is the other bn. And then the final result of result of the analytical analysis, analysis, analysis is the Fourier transform. I'm sorry, guys. My battery is almost done. Pardon, pardon. So let's continue this. This T is also a numerical or is it iterations, right? It has this variation because the Bn is equals to sin h, sin hyperbolic of those and the sin hyperbolic of the s. So in this sin hyperbolic of the s, it is the sin hyperbolic n per n times phi, n times phi. So yeah, this is actually not in phi. I'm gonna write it as that. So this is the final result of the analytical analysis. This is a Fourier transform or Fourier theorem, Fourier function. And then in the numerical analysis, let's get to the numerical analysis. Numerical analysis. In here, I'm gonna use a Lightman method because what? Because this is not complicated. This is the problem that I am encounter is not complicated and it's just two-dimensional and the iterations is just 17. So I don't think I'm gonna use like the Gauss-Seidel method because that is more likely to be more in the this is we don't have a lot of data, a lot of data. We don't produce a lot of data because I just the iteration is just some it's just 17 and plus and the mostly is 17 plus 1 is 18 and I don't think this is worth it and I don't think using the Gaussian is more accurate like in the matter of the accuracy is not like far from this Laban method because this is just two-dimensional and then we don't have the vast amount of data and also the in the site in the same site the temperature is not differentiate. So yeah, I'm gonna use the Laban method in an explicit way, explicit, explicit. So from the BDE, from the BDE or let's say of this one, right? I'm gonna write this one again. I'm gonna use it as T because we calculate the distributions of temperature over the plate of the metal of the iron with the T is equals to, in this is the numerical way, numerical analysis. No, 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 no. Okay, this is the temperature of the E plus 1 J. This temperature of iteration from the we have matrix in this case. We have matrix, and the to calculate it, we need the in row first, but class first is a second. So it's a second. If the row one, we got the second. For the J, for the movement is E and then J. The movement is from E to J. So this, and of course with this have this E from J, of course, and then it is the old minus 1. This is the old iterations that we got. This is one, the new one. This is the old one, and this is what we got now. So the delta x squared. And then for this y, y is, because the y is in row of, it's not row, but in column. So J is a column and Y represent column because the J is horizontal and the vertical is the X. So the same here, J is minus 1. So if we see these equations, we can get was this equals to 0. And then when let's say if the delta x one delta x is equals to delta y, you can get this equation. Four is equals to, of course, 0. And then if we wanna calculate the t, this one, we can get the equations. of, yep, we have these equations. And then these equations in the numerical way can be touched as, this is the new one. So we actually have the lambda here. This is the constant. I'm sorry, guys. It's not really practical anymore. This is the old one. So lambda, where's the lambda that I've been talking about? But this is different from that lambda, from this lambda. This is different from this lambda. And then we got this uh numerical analysis. This is the numerical analysis to solve the distribution of the heat on the metal plate, two-dimensional metal plate. And before we knew this is before we dive into these equations, this is actually we first need to generate or we need to make a matrix. And if we uh, analytically or conventionally do this on paper, this is would be take a long time, and sometimes the result is not as accurate because this is actually a lot of data for a conventional calculation. So we need the computational to work this out, and I will do it right now in Octave. So yeah, let's say, okay, fine. I need to create the parameter that we need. Make parameters. PL is equals to 20 centimeter, and then T rate. T rate is equals to 101. T top, we have T top also. Top is 17 degrees Celsius. And then the rest is T left, 0. And the T right, no, the bottom is over 0. But I don't want to. But we have the T initial as 0 as well. So yeah, 0. And then the range. In the actually in this problem in these cases, we we already serve by range, but the range is 55. Like I don't get it. I can work this out, so I'm just gonna make it the part, the sub part of the PS with the n. So the I have the n as 17. Now I'm gonna initiate matrix, initiate matrix. I'm gonna initiate the matrix with the zeros, zeros of the n plus one n plus one. So, and then we have to set the boundary condition. Condition because just this side is 101 degrees Celsius, and this side is 70 Celsius, this side is zero, and this side is zero. So yeah, this is not really practical anymore, but I'm gonna show it. To n, and then to one, and then to left, this is zero, and we have the n, this it's the top, the 71. Mm, two, one, again, which equals to the top. So now we calculate the method, like Lippmann method here. Method, okay. Okay is one, two, n for the, the e is equals to one, not two, to n. For j is two, also two to n. So we need to insert the equations that we already got in numerical analysis, the TIG1, the EG1, the IG1, because we already have this is the lambda, and not the lambda, this is the K of the diffusion thermal or the conductivity thermal. Nine one or minus one point J plus two F E plus one point J E E D. 1, 2 plus 1 and 4, and then this is already done, the method, and then we have to show display the matrix distribution matrix. Matrix. Wait here. And then we also want to see the graphic. So we're gonna show the graphic. This is the 3D graphic, 3D graph. No, this is the, I'm gonna, no, because this is how we done it. I'm gonna make it as two-dimensional first, and then I'm gonna make it colored, so it can be differentiate how the on a plate the heat is distributed, and then I will make the 3D graphic to enhance the visual. Yeah, wow, figure. I'm gonna use the contour one. So in here I just want to go the range so we can. I'm gonna use the quiver functions to do the to make a flow, and make the flow visible. And then I'm going to display the 3D one so we can see more like placing visually. I'm going to use the main script one. Mhm. Mhm. Main script. Main script. One, two, and plus one. One. Of course, this is also the one to the end and plus one. Plus one. Here. I'm gonna use the serve. Oh, I'm not coloring it up. So yeah. Okay, let's try this and hit flow. Okay. Oh, yep. This one. Oh, sorry. Okay. I think I'm doing something wrong here. Okay. Yep. Wait. Here, control off. Here, control. Control. Oh, you're right. Yep. Okay, we can see here that this is the metric distribution that I've got. So the below, this is the top one. The top one is 17 degrees, and then this is 101 degrees. Then this is zero, and then this is also zero. So we get this contouring of the plate. This is in the plate, like the The temperature is come from here, and from a little bit from here, 17, and it's 101, and then coming to this distribution. So the 3D distribution, we have this. So yeah, uh, that is the end of my presentations of my uh, video in this uh, problem. Thank you for enjoying this video, and hope to see you in the next video again. And warm welcome to me. Wassalamualaikum warahmatullahi wabarakatuh.